The most valuable material in an electric car battery is lithium, and the world has spent 15 years fighting over who controls it. Mines in Australia, brine pools in Chile, refineries almost entirely in China. In April 2025, a Chinese company announced a battery that doesn't use any of it. No lithium, no cobalt, no nickel. It runs on sodium, which is one of the most common elements on Earth, and you can buy it by the ton for almost nothing. It's in production now. Here is what it actually does, and the part nobody wants to talk about. The battery is called Naxtra, made by CATL, the company that produces roughly a third of the world's electric vehicle batteries. The headline number is an energy density of 175 watt-hours per kilogram, which matters because that puts it within striking distance of the lithium iron phosphate batteries currently powering millions of affordable electric cars. Sodium ion was supposed to be far behind that. CATL also claims around 10,000 charge cycles, which is roughly 3 times what a typical electric car battery is rated for, and enough that the battery would outlast the vehicle. And it operates down to minus 40 degrees Fahrenheit while still delivering about 90% of its power, which no lithium battery can come close to matching. To understand why anyone bothered, look at the supply chain. Lithium is not rare exactly, but it is concentrated. It comes from hard rock mines in Australia or evaporation ponds in the Atacama Desert, both of which take years to permit and build. And the refining that turns raw ore into battery-grade material happens overwhelmingly in China. Sodium has none of those problems. It comes from soda ash and ordinary salt. It's about 1,000 times more abundant in the Earth's crust than lithium, and it's already produced at industrial scale worldwide for glass and chemicals. There is no sodium cartel. There is no sodium price spike. If you can make a good battery out of it, the geology stops being a strategic weakness for anybody. So why didn't this happen 20 years ago? Because of one physical fact. A sodium ion is bigger than a lithium ion. Substantially bigger, about a third larger in radius. In a lithium battery, ions slot themselves into the layered structure of graphite in the anode, sliding between sheets of carbon like cards into a deck. Sodium ions are simply too large to fit comfortably into graphite that way. Push them in, and the structure strains and degrades, and the battery loses capacity fast. That single geometric problem is why sodium-ion batteries stayed in laboratories for decades, while lithium went on to power the entire modern world. The chemistry wasn't wrong. The material it needed didn't exist yet at any usable quality. The solution was to stop using graphite entirely and switch to something called hard carbon. Hard carbon is a disordered form of carbon with a messy, irregular internal structure full of gaps and pores rather than neat parallel sheets. Those irregular spaces are large enough to accept sodium ions without straining, and that turns out to be exactly what sodium needed. The problem was making hard carbon consistently, at scale, and cheaply from feedstocks like biomass or petroleum coke, with reliable pore structure batch after batch. That's a manufacturing problem rather than a science problem, and manufacturing problems are precisely what Chinese battery firms are best at solving. On the cathode side, most sodium designs use either layered transition metal oxides or a class of materials called Prussian white, neither of which needs cobalt or nickel, which removes 2 more contested supply chains from the picture. Now, the genuinely interesting advantage, which has almost nothing to do with cost. Sodium batteries work in the cold, and lithium batteries really don't. Anyone who has driven an electric car through a northern winter knows this. Range drops 30 or 40%, charging slows to a crawl, and the car spends energy heating its own battery before it can accept power. That happens because the electrolyte thickens and lithium ions move sluggishly through it at low temperature, and if you force charging anyway, you get lithium plating on the anode, which permanently damages the cell. Sodium chemistry doesn't suffer nearly as badly. Sodium ions move more freely at low temperature, and KTL's claim of 90% power retention at minus 40 Fahrenheit is not a small improvement over lithium. It's a different category of behavior. For Canada, the northern United States, northern Europe, and northern China, this is not a marginal feature. It's the whole argument. There are two more advantages that don't show up in headlines. The first is safety. Sodium cells are considerably more tolerant of physical abuse, and CATL has demonstrated cells being drilled through and cut without igniting. That's not a stunt for its own sake. It changes how much protective structure, cooling, and fire suppression a battery pack needs, which takes weight and cost out of the entire vehicle. The second is a quiet manufacturing trick. Lithium batteries require copper current collectors on the anode side because aluminum reacts with lithium. Sodium doesn't have that problem, so you can use aluminum on both sides of the cell. Aluminum is cheaper than copper and significantly lighter, and copper is one of the tightest supply constraints in the entire energy transition. Removing copper from a battery is worth more than it sounds. Now the trade-off, because there is always one. Sodium is heavier than lithium as an element, and sodium cells operate at a lower voltage, around 3.1 volts against roughly 3.6 or 3.7 for lithium chemistries. Both of those work against you, and they combine into lower energy density at the pack level. In practical terms, a sodium-powered car carries less range for the same battery weight or the same range for a heavier and larger battery. 175 watt-hours per kilogram is genuinely impressive for sodium, but high-nickel lithium cells for premium vehicles reach 250 to 300. So sodium is not going to power a long-range luxury electric car. It was never going to. It's aimed at city cars, at commercial fleets running fixed routes, at heavy trucks, and at grid storage where weight barely matters at all. And here is the catch that undercuts the entire story, which almost no coverage mentions. Sodium ion's biggest selling point was always supposed to be cost, and right now, it isn't cheaper. Lithium prices spiked enormously in 2022, which is exactly when sodium-ion research funding exploded, because suddenly the economics looked obvious. Then lithium prices collapsed, falling by around 80% from that peak, while lithium iron phosphate production scaled to enormous volumes with fully mature supply chains and factories already paid for. Sodium ion, meanwhile, is manufacturing at a tiny fraction of that volume with a hard carbon supply chain that barely existed 5 years ago. The material inputs are cheaper. The finished cell today is not. That's why the first real commercial deployment isn't cars at all. It's replacing lead-acid starter batteries in heavy trucks and grid storage installations where sodium's cold tolerance and cycle life win on their own merits without needing to be cheaper per kilowatt hour. So what is this actually worth? Not the death of lithium, whatever the headlines say. Sodium and lithium are going to coexist, splitting the market by use case, the way lithium, iron, phosphate, and nickel chemistries already do today. What sodium buys is optionality, and that's a strategic asset rather than a technical one. A country with working sodium-ion manufacturing can never be squeezed on lithium supply because it has a functioning alternative sitting on the shelf ready to scale. That's worth having even if you never fully deploy it. And notice what building it required. Not one breakthrough, but a hard carbon supply chain, cathode material production, electrolyte formulation, cell manufacturing at scale, and customers willing to buy the first imperfect generation. Every one of those is a factory, and factories take a decade to build and fill with people who know what they're doing. The battery is the visible part. The 20 years of industrial capacity underneath it is the part that actually took the work